Welcome to the module Heat Engines and Second Law of Thermodynamics. In this module, I will introduce you to the origins of thermodynamics and outline the historical studies of heat engines that led to the development of the second law of thermodynamics. The question of reversibility and irreversibility was first addressed in the work of Sadi Carnot in the year 1824. His work on the efficiency of heat engines is considered the foundation of thermodynamics. Thus, it could be argued that thermodynamics began with the second law. However, this does not mean that the principle of irreversibility comes before the principle of the conservation of energy. This would have been logically inconsistent, as the irreversibility can only be perceived within the framework provided by the conservation of energy. In fact, in Carnot's theory, the impossibility of generating work out of nothing plays an essential role. Heat engines are devices that convert heat released in a combustion process into mechanical work. A real-world example of a heat engine is an automobile's internal combustion engine, which operates through a cyclical process involving fuel intake, compression, ignition and expansion, and exhaust. These processes occur thousands of times per minute, generating work on the surroundings by converting the heat released from combustion into mechanical motion. An idealized model of a heat engine is depicted in this figure. In this model, the system consists of a working substance, such as an ideal gas, confined within a piston and cylinder assembly with diathermal walls. This assembly can alternatively be brought into contact with two thermal reservoirs: a hot reservoir at temperature T hot and a cold reservoir at temperature T cold. When the assembly contacts the hot reservoir, the gas expands due to the increase in temperature, driving the piston outward. Conversely, when the gas is in contact with the cold reservoir, it contracts, causing the piston to move inward. The linear motion of the piston, generated by the expansion and contraction of the gas, constitutes the work output that can be used for various practical purposes, such as powering a car's movement. Experience shows that converting work into heat can be done with 100% efficiency. All the work done on a system can be entirely converted to heat, resulting in an increase in temperature. However, the reverse process of converting heat into work cannot be achieved with 100% efficiency. This efficiency quantifies how effectively a heat engine can convert heat into useful work, which is crucial for practical applications of heat engines. The limited efficiency of heat engines is not due to flaws in their design, but rather because there is a fundamental asymmetry in nature. While work can be fully converted into heat, heat cannot be fully converted into work. This natural asymmetry is a manifestation of the principle of irreversibility, which is a core concept of the second law of thermodynamics. Using the second law, thermodynamics explains that there are inherent limitations on the efficiency of heat engines. Sadi Carnot sought to explore this natural asymmetry between work and heat in the early 19th century. As an engineer, Monsieur Carnot had his own unique perspective on the underlying principle of irreversibility that we now refer to as the second law of thermodynamics. For Carnot, this principle was deeply connected to the efficiency of heat engines. Carnot's analysis began with two fundamental questions. Is the motive power of heat, la puissance motrice du feu, or in other words, mechanical work produced by a heat engine, inherently limited or is it unlimited? The second question that he posed can be formulated in modern terms as: can the efficiency of a heat engine be increased by using a different working medium? By medium, Carnot referred to the working substance inside the heat engine, a gas that undergoes expansion and performs mechanical work. In his foundational work, Carnot begins by discussing the steam engine, a technology that was widely used in the early 19th century. Carnot's analysis of the steam engine formed the basis for his theoretical exploration of the efficiency of heat engines and ultimately for the development of the second law of thermodynamics. According to Carnot, the steam engine operates on the following principle. First, heat is generated in the firebox by burning fuel, such as coal. This heat passes through the walls of the boiler, where it causes water to boil and produces steam. Then the steam enters the cylinder, where it expands. This expansion pushes a piston, producing mechanical work, which Carnot refers to as motive power. After performing work, the steam reaches the condenser, where it comes into contact with cold water. The steam condenses back into liquid water, releasing heat in the process. As Carnot explains, the cold water in the condenser ultimately absorbs the heat that was produced by combustion. According to Carnot, the production of work in a steam engine is not achieved by the direct consumption of heat, but rather by its transfer from a hot body to a cold one. This principle applies to all heat engines. In other words, heat alone is not sufficient to produce work. A cold body is also required, or more generally, a temperature difference is necessary. Wherever a temperature difference exists, work can be produced, notes Carnot. The heat released by the condensed steam to the cold body can, with an input of work, be transported back to the hot body. In this way, the process becomes a cyclic process. The work produced in such a cyclic process reaches its maximum when all possible losses of work are minimized. This occurs when a reversible thermodynamic process is considered. However, a truly reversible process is a theoretical construct that is not feasible in reality. Carnot described such a reversible cyclic process in detail. From his analysis, we can answer the first fundamental question. The maximum work that a steam engine can produce is indeed limited. Furthermore, even this upper limit of work, which is theoretically achievable in a reversible cyclic process, cannot be reached in a real-world cyclic process operating under the same conditions. In practical applications, various inefficiencies prevent real engines from achieving this theoretical maximum. After analyzing the theoretical reversible cyclic process, Carnot provided a negative answer to the second fundamental question regarding the efficiency of heat engines. The conclusion drawn from Carnot's analysis is that the efficiency of a reversible heat engine cannot be improved by using a different medium. If there were a working substance that could produce more work than another under the same temperature difference, it would imply that some heat could be converted directly into work without the need for a cold reservoir. This would contradict the previously established principle that a cold reservoir is required for the conversion of heat into work. Therefore, such a substance does not exist. We can conclude that the maximum theoretical efficiency of a heat engine is independent of the specific working substance employed. No matter what medium is used, whether it is water vapor, an ideal gas, or any other substance, the maximum efficiency achievable by a heat engine operating between two temperature reservoirs is the same as long as the engine operates reversibly. This outcome confirms Carnot's conclusion that the maximum efficiency of a heat engine is a universal characteristic determined by the temperature difference between the heat reservoirs rather than the specific properties of the substance involved in the cycle. Carnot's results can be summarized in a few key points. First, no heat engine operating between two thermal reservoirs, one for heat supply and one for heat removal, can have a higher efficiency than the efficiency of a reversible Carnot engine operating between thermal reservoirs at the same temperatures. The latter is often referred to as the Carnot efficiency. Second, all reversible heat engines will have the same efficiency as a Carnot engine operating between the same temperatures. This means that the efficiency of any reversible engine depends only on the temperature of the heat reservoirs, not on the specific properties of the working substance or the details of the process itself. Finally, any irreversible heat engine has lower efficiency than a reversible Carnot engine operating between the same temperatures. These results provide a fundamental understanding of the limits of efficiency that any heat engine can achieve. However, they are also important for us in a broader context than it appears. Specifically, these statements constitute one of several equivalent formulations of the second law of thermodynamics, as originally expressed by Carnot. The study of heat engines and their limitations in the 19th century led to an alternative but nevertheless equivalent formulation of the second law of thermodynamics, known as the Kelvin-Planck statement. According to this formulation, it is impossible for a system to undergo a cyclic process whose only effects are the flow of heat into the system from a heat reservoir and the performance of an equivalent amount of work by the system on the surroundings. No heat engine can extract heat from a single thermal reservoir and convert all of it into mechanical work without any other effect, such as the rejection of some heat to a colder reservoir. This concept is visualized in the figure. Part A on the left shows a schematic model of a heat engine operating in a reversible Carnot cycle between a hot and a cold reservoir. In contrast, Part B on the right illustrates a hypothetical engine that would extract heat from a single hot reservoir and convert it entirely into work. According to the second law, such an engine cannot be constructed, as it violates the principle stated by Kelvin and Planck. This formulation highlights the necessity of a temperature difference for the conversion of heat into work, emphasizing that a cold reservoir is essential in any real heat engine cycle. In addition to the Carnot and Kelvin-Planck statements, there is yet another equally valid formulation of the second law of thermodynamics proposed by Rudolf Clausius. This alternative statement focuses on the natural direction of heat flow and states that it is impossible to perform a process whose only result is the transfer of heat from a colder body to a hotter body. In other words, the Clausius statement emphasizes that heat does not flow spontaneously from a colder body to a hotter body. Without external work being done, heat naturally flows from a hot object to a colder one and not in the reverse direction. This formulation of the second law is important because it highlights the inherent directionality of heat flow and reinforces the concept of irreversibility in thermodynamic processes. It emphasizes that thermal energy transfer always tends towards thermal equilibrium, where temperatures are uniform.